resistor to a DC circuit, right? So, or you are connecting a resistor with one capacitor in a DC circuit, right? And you found that because this is a DC circuit, so the voltage across, okay, for example, I'm just referring to RC circuit, right? So here is the RC circuit. The voltage across the resistor is VR. Voltage across the capacitor is VC. So if this is a V of a DC source, all right, DC supply of the V, then I can express the expression of, okay, voltage supply is equal to the voltage across the resistor plus voltage across the capacitor in DC. Okay, because they are connected in series. And now we are consider the case where you connect the resistor, a capacitor, and also an inductor with the AC circuit, right? So this is C and this is L, okay? So voltage across the resistor is VR, voltage across the capacitor is VC, and voltage across the inductor will be VL. But this is an AC circuit. AC means the voltage here is actually V equal to V naught sine omega T. The maximum value of the V naught, right, is not equal to the voltage, maximum value voltage across the resistor plus the maximum across the capacitor plus the maximum across the inductor. Okay, it is not, right, due to there is actually a phase difference between the R, voltage across the R, voltage across the C, and voltage across the L. So today we are going to focus on this. How are we going to get the relation, right, between voltage across these three components? Okay, now firstly, we consider a pure resistive circuits, right? Pure resistive circuit means I have one resistor which has the resistance only, right? And is connected to an AC source, right? It's connected to an AC source. And frequency, for example, frequency of this generator is F, right? F, it could be 50 hertz, it could be 100 hertz, it could be 1 kilohertz, and so on, right? So we can use the voltage VRMS, voltage root mean square, is equal to IRMS multiplied with R, which is Ohm's law. Okay, VRMS is equal to IRMS multiplied with R. Ohm's law said that V equal to IR. Okay, now I have only one component of electronic component of R, right? So VRMS is equal to IRMS multiplied with R. So of course, V maximum is also equal to I maximum multiplied with R, because IRMS is equal to I naught divided by root 2. Okay, so how about the frequency? What is the relation between the frequency and the resistor here? Will the resistance change if the frequency change? The resistance across versus frequency is actually a constant. Let's say you're connected oscilloscope to observe what is the voltage across the resistor. Okay, so the voltage across resistor, it is in a sine waveform. Because the power supply here is sine waveform, right? The voltage here is in the sine waveform as well. And however, the current across the in this circuit is also in a sine waveform. So this one I call it as I. Here is the voltage of V, right? So we can conclude that for the pure resistive circuits, V and I, the voltage and I are in phase, right? In phase means there's no phase difference. The current will reach the maximum at the same time as the voltage reach the maximum. Voltage and current are always in phase. Okay, now the next one, we consider a pure capacitive circuit, or just simply as capacitive circuit also can. I'm connecting a capacitor, where this capacitor, there's no resistance, there is no inductance in the capacitor, but it only have a capacitance, right? And connected to a AC source. Ohm's law said that V equal to IR, but there's no R here, right? But there's one term we call it as capacitive reactance. So this XC, we call it as capacitive reactance, which has similar to resistance, but is complicated than resistance because the value of the capacitive reactance, it depends on the frequency, right? So the unit for capacitive reactance is in the unit of ohm. I apply Ohm's law. The V here I refer to VRMS. Here is also IRMS. Capacitive reactance, all right, is vary with frequency, where XC, or the capacitive reactance of XC is equal to 1/2 pi FC. Therefore, if you plot the graph, XC versus frequency, you will get this type of graph, right? Because XC is inversely proportional to the frequency. The higher the frequency, okay, and then the lower the capacitive reactance. Okay, what happened to the phase difference, okay, between the voltage and the current, right? And if let's say you are using a oscilloscope to observe the waveform, it is found that, right, the voltage across the capacitor is still in this form, VC, but the current flow in the capacitive circuits will actually leads, right? This is the current. So then we will say that the I leads voltage across the capacitor by 90 degree. By 90 degree means pi over 2 radian. So this graph, yeah. Current reached the maximum at T1 here, right? So the voltage reached the maximum 90 degree phase later, right? That means current will reach the maximum 90 degree earlier if you compare with the voltage. So that's why I is leading the VC by 90 degree, right? This is a phase difference between the I and the voltage across the capacitor. In the other words, you can say that V lags I by 90 degree also can, right? Either I leads the VC by 90 degree, or V lags I by 90 degree also can. Okay, so next one, we are going to investigate or consider an inductive circuit. Inductive circuits means I'm connecting a inductor, a coil, to an AC source, right? So the inductor has an inductance of L. The AC circuit, we have V RMS equal to I RMS multiplied with R, but there's no R here, right? This is a pure inductor, so it only consists of reactance. So we call it as inductive reactance. The symbol is XL. This one is inductive reactance, which has the unit of ohm. So inductive reactance also depends on frequency, right? Where XL is equal to 2 pi FL. It is proportional to the frequency. Inductive reactance is proportional to the frequency. Therefore, when you plot a graph, inductive reactance versus frequency, you will get one straight line, right? Because XL is equal to 2 pi FL. As the frequency increase, the inductive reactance will be also increased. Okay, and the phase difference between the voltage across the inductor and the current flow through here also is not in phase. So in this case here, the voltage across the inductor is VL, okay, and the current is actually lags the V by 90 degree. So the current lags the V means will be something like this. Okay, this is the I. So we'll say that I lags V across the inductor by 90 degree. If I combine, right, these three individual circuits to make it as RCL series circuit. It can be RCL or RLC, it doesn't matter. RCL or RLC series circuit. Okay, I combine, so it means I'm connecting the R, the C, the inductor in series with an AC source, right? So the voltage across the resistor is VR, voltage across the capacitor is VC, voltage across the inductor is VL, right? So I know that the current flow in this circuit is always I, right? Voltage across the resistor is VR. The current are in phase. So this one I call it as phasor diagram. Represent the phase difference between the I and the V. Okay. So just now I was mentioned that the VC is always lags behind, right? VC is lags behind. VC lags I by 90 degree. So VC lags I by 90 degree means VC will be here. Okay, this is 90 degree. Okay, this here is I, right? This one is I. So VC lags I by 90 degree. Then I lags VL by 90 degree. I lags VL by 90 degree means I is already here. So lags VL by 90 degree. So I know that VL will be here. Right? So this one actually is the maximum value. So I use not to represent the maximum. This is the maximum and here is the maximum. Okay, the length here, what is the length of this arrow is actually referring to the maximum value of the voltage across the resistor. Right, that's how you draw, how you see the phasor diagram. So you can also draw the phasor diagram. Not necessary this I will be always horizontal. Okay, you can rotate in any direction that you want. You can draw the phasor diagram something like this also can. Okay, let's say this is your phasor diagram. Okay, I can accept it if you feel that this is easier for you to refer. Okay, effective resistance in this RLC series circuit. All right, so the effective resistance, we don't call it a resistance because in an inductor and a capacitor, so-called as a resistance, we call that reactance, right? And therefore, in this RLC series circuit, this effective resistance, we have a term called it as impedance. Symbol is capital letter of Z. Symbol is capital letter of Z, impedance, okay? Impedance, Z, is equal to Vrms divided by Irms. I'm applying Ohm's law. V equal to IR. So instead of R, I have the impedance. Again, this diagram is called as phasor diagram. Phasor diagram. VL0 and this VC0 actually is, the difference is 180 degree, right? So I can combine to make it as only phasor diagram with two components. Then here will be VL0 minus VC0. Right, because the difference between the VL0 and VC0 is 180 degree. So I combine it to make it as VL0 minus VC0. Right, not is the maximum value. Here is also always equal to VR0. As the resultant of the voltage is actually the maximum voltage of V0. So this V0 is referred to here. This is the AC source. So AC source is V equal to V0 sine omega t. So this is the V0, which is the maximum value of V0 here. Right? So based on this phasor diagram, V0 is equal to VR0 square plus VL0 minus VC0 square root of it. Am I right? It's just like a vector, very similar to vector. I'm using the Pythagoras theorem to find out what is the V0, which is the V maximum of the source. Okay? Then, by applying Ohm's law again, V equal to IR. So I have I0 square R square plus V equal to IR again, so I0, right, R, but R in across the inductor is not resistor, but it is referred to the reactance. So reactance, we have the symbol of XL minus IXC square root. All right, then I further simplified it, I0 square R square plus, this is I0, this one also I0 is a common factor, so I factored it up because it's square there, so I squared it. XC, inductive reactance, minus, XL minus XC square, and square root. I0 square root of R square plus XL minus XC square. So this is V0, right? So I compare with Ohm's law. Ohm's law is said that V0, V is equal to IR. So V0 is equal to I0 Z. And therefore, the impedance of Z is equal to R square plus XL minus XC square root of it. That is how you get the impedance in a RLC circuit as this expression. So of course, in this RLC series circuit, the expression of V0 equal to I0 equal to multiply with Z is valid. Expression of this also valid. Vrms is equal to Irms multiplied with Z, right? Because Vrms is V0 divided by root 2. Irms is I0 divided by root 2 multiplied with Z. Okay, and the root 2 you cancel off, so you will get back this expression. We can actually also find out what is the average power delivered. Okay, average power delivered to the circuit. Okay, current flow in the circuit will be always the same because it is in series. Power delivered to the circuit. So this power is called as average power to AC circuit. In a DC circuit, the average power in DC, if you still remember, in the DC circuit, CCT means circuit, average power is actually same as Vrms multiplied with Irms. That is the average power of a DC circuit. So average power of an AC circuit not equal to Vrms multiplied with Irms only, but you have an additional term of cos phi. So this term, we call it as power factor. Okay, the term we call it as power factor. And of course, it can be also expressed in this way. Average power is also equal to I RMS square multiplied with Z. Then you have an additional term of cos phi as well, which is also called it as power factor. Okay, power factor, dissipated power. All right, power only dissipated in resistor only, dissipated only by resistor. There is no power can be dissipated in inductor or capacitor, right? And therefore, the average power dissipated in resistor is I square RMS multiplied with R. Okay, we don't multiply with Z because power only dissipated in resistor only. Okay, so what is this power factor? Okay, what is this power factor? You can refer back to the phasor diagram. So if you refer to this phasor diagram, okay, you can see that there is one phi here. Okay, phi is actually the angle between the VR and the V naught, right? Angle between the VR and the V naught. So if I draw, put it horizontal. Okay, put it horizontal like this. So angle phi is actually angle between the VR and the V naught. I refer to this triangle. Tangent is equal to, so opposite divided by adjacent. Opposite is actually VL minus VC, right? Adjacent is VR. Okay, this is the maximum. So VL naught, VC naught, and VR naught, right? The length here is actually the maximum value across the resistor. This one should be not and not, not and not. Okay. Then we know that according to Ohm's law, V equal to IR. So voltage across the inductor would be I RMS multiplied with XL minus I RMS multiplied with XC, because V equal to IR, so this is V, it will be I multiplied with XL, V equal to IR, so this is V IR, so I RMS multiplied with XC, then divided by V equal to IR again, so I RMS multiplied with R. Okay, so here is actually use Ohm's law to find out the relationship. And from here, tangent phi is then equal to, so in a RCL series circuit, the current flow through will be the same because they are connected in series. So all the IRMS cancel off, and eventually you will get XL minus XC divided by R. Okay, this is actually the so-called as the tangent phi, right? And cos phi, so based on the same triangle as well, cos is VR naught divided by V naught. Here is phi. So here will be opposite. Tangent is opposite divided by adjacent. So therefore, cos phi. Here will be the impedance, right? Cos phi is equal to adjacent divided by the impedance. Resonance occur in mechanics. So the pendulum, maybe it has a maximum amplitude, right? Okay, this is in mechanics. But in AC circuit, we can also have resonance. So resonance occur means the RMS value will be maximum. RMS value will have a maximum value, right? So now we're going to find out how can we calculate the resonance frequency in AC circuit, right? So if you make a comparison, okay, let's say I'm referring to a graph versus frequency, okay? You'll find that this root mean square current, right? Root mean square current in AC circuit, okay, it will actually vary, right? It will not fix at one value, but it will vary with frequency in this form, right? It will reach a maximum value at a frequency, we call it as resonant frequency. So let's say this is resonant frequency. Right, so here I call it as IRMS maximum. It's not the I maximum, but it's called it as IRMS maximum because this blue color line is actually representing the IRMS. So the IRMS value will reach the maximum at resonance frequency. So at this point as well, the impedance of the circuit will actually minimum, right? This one is impedance, right? At this point, it's minimum. Z is minimum at resonant frequency. In RLC series circuit, so we know that IRMS is equal to VRMS divided by Z, right? From Ohm's law, V equal to IZ. So this one is RMS, here is RMS. Therefore, IRMS is equal to VRMS divided by Z, where Z is actually the impedance. All right, where Z is equal to R square plus XL minus XC square root. So R square plus XL is 2 pi FL minus 1 over 2 pi FC square. At resonant frequency, IRMS is the maximum, impedance will be the minimum. So if you refer back to here, actually it makes sense. When IRMS maximum, Z will be minimum. So how do I get the minimum of Z? You can see from this expression, R is independent on frequency. Only the capacitive reactance and inductive reactance depend on frequency. At resonance frequency, okay, to get Z as minimum when the inductive reactance is equal to the capacitive reactance. How can you get Z as minimum? So when this term is minimum, how can you get this as minimum? R is independent of frequency, so you cannot change the value of R, right? But capacitive reactance and inductive reactance depends on the frequency. So to get the Z minimum means this one must be 0. How can I get this 0? When the capacitive reactance is same as the inductive reactance, right? So in the other word, at resonant frequency of F0, XL minus XC is equal to 0, right? Because I want to get the Z minimum. Okay, this time 0 means XL is same as XC, right? So which means 2 pi FL is equal to 1 over 2 pi FC. This is the frequency at resonant frequency. So I have to replace this with F0, this with F0, right? Then I cross multiply, I will get F0 squared is equal to 1 over 4 pi square LC, right? And therefore, resonant frequency is 1 over 2 pi square root of LC. This is the resonant frequency for an AC circuit. At resonance frequency, okay, let's say I refer back to the power factor, right? So power factor, we have the phi, tangent phi, it is defined as XL minus XC over R, right? So at resonant frequency, equal to F0, right? And XL is equal to XC, and therefore tangent phi is equal to 0. Tangent phi is equal to 0 when phi is also equal to 0. At resonant frequency, cos phi, which is equal to cos 0, is equal to 1. So the power factor is always equal to 1 at resonant frequency. That means at resonant frequency, the power delivered to the circuit is actually the maximum.